Okay, sorry about the delay. My Dropbox wasn't syncing, so I had to do it the slow way. Okay, so we're going to talk today about parallel programming. How many people started on milestone 4 anyway? Okay, one at least. How did milestone 3 go? Go okay? So, okay. Was it fun? Painful? Maybe you can't tell me. Maybe you have to use the anonymous feedback link. What do you think? So you're going to have the course evaluation soon. So if you've got comments, write them in there. We read them carefully. So if you're like, oh, this was super painful or this was super fun, tell us. Okay, so it sounds like everyone's too shy to give any feedback. So maybe you'll give it in writing. Okay, so let's talk about parallel programming. Okay, so a quick review of milestone 4. So you're doing this traveling courier problem, so a variation on traveling salesman. You've got depots where you start and end. You've got pickups, you've got drop-offs. And you're trying to find the fastest delivery route. And a sub-piece of that, which we're going to use as our example of how you multi-thread something, is we need travel time between various locations, right? So we'd like to know what would the travel time be between these 2 points. Maybe those are 2 deliveries. So we can decide, should we do that? Or maybe we'd be better off with an order that went to this one instead. Okay, so we're talking about a sub piece of M4 here. And then we're going to use that to help us get a good delivery ordering. Okay, and we got to do this whole thing in less than 50 seconds. So if we were able to use multiple CPUs, we could get more work done, right? So we have more time to try more things, hopefully get a better answer. Okay, so we talked about this in lecture. If we want to estimate travel times, we've got K interesting intersections. Okay, so in a city like Toronto, we've got maybe 150,000 intersections. But the ones that are really interesting to us are the ones where they're a depot or they're a pickup location or a drop-off location. And the number of those is a lot smaller, right? So for a big problem we give you, there might be 300 of those interesting intersections. And those are the ones where we're going to want to be able to get what's the travel time between them. We talked in lecture about a fast way we could do that is just estimate by distance. It's fast, it's easy, but it's not going to be perfectly accurate, which will cost you some amount of quality because you'll make some decisions that aren't the best. Other way we could do this is we could go figure out what is the actual path between different intersections, like the fastest travel path using your M3 functions. And that can get you somewhat better quality, but it's slow. And the idea with that one is, well, maybe we can pre-compute for every from intersection. And again, it's only the interesting ones. So this matrix is not enormous. It's maybe 300 by 300, which isn't a really big deal to store. So storage isn't a problem. And from interesting intersection 1, we could get, well, what is the best travel time to every single other interesting intersection? Whoops, sorry, let me change this. To every other interesting intersection in the problem. So from intersection 1 to intersection K, right? This is like an interesting intersection index, okay? So it's a new index, it just goes from like 0 to 300 or so. Okay, and then if I want, intersection 2 to everybody else, well, I'd go to row 2. Row 2 is going to give that information. Row 3 is going to give it starting at intersection 3 and so on. Okay, so if I had this matrix, I could very quickly figure out the travel time from any of my interesting intersections to any other one and use that in my optimization of delivery order. Okay, so how do I get this matrix? So we should pre-compute it because we might use it a lot. And this is a bit of review from lecture. So if you're paying careful attention to lecture, you kind of like already know this, but let's review it quickly. So you can use your milestone 3 function to do this. And your best milestone 3 function, if you went this far, is you wrote an A-star algorithm. And an A-star algorithm fundamentally takes a starting point, so source intersection, and it takes an ending point, a destination intersection. And it's going to search through the city to find what's the best travel path between them. And what I'm doing here is I'm basically going through for all of the start intersections. So every interesting intersection as my start point. And then for every interesting intersection as my end point, go and fill in one entry in that matrix, which we're calling paths, using my milestone 3 algorithm. Okay, so everybody with me, right? And a matrix is just a vector of vectors. So it's not a really complicated data structure. Okay, so let's quickly calculate the complexity of this. So we've got K of these interesting intersections, and then we've got V total intersections in the whole city. So V stands for vertex. What do you think the complexity of this is? It's not that hard. Okay, so look at it and kind of go, okay, does anybody want to take a shot at this? If not, I'm going to start giving you hints until somebody takes a shot at it. So what do you think? We're all friends here. It's a safe space. Don't worry. If you get it wrong, it's low stakes. Okay. So what do you think? What do you think the complexity of this is? Sorry? I couldn't hear you. Can you say it really loud? N squared. So I didn't put N on here. Which one is N? So I'm using K to mean like, I found N was vague in this case. So I'm using K to mean the number of interesting intersections. Do you mean K squared or do you K squared? Okay, so you're right. It is K squared because we've got these two loops. So we've got a K squared in it. Now in the middle of this loop, we've got this. Okay, so that's not an order one operation. So now we've got to figure out what that is. So what do you think for that line? So I'm with you with the K squared, but now this find path A star is not constant time. So how big is it? So anybody remember? So for an A star algorithm, it's faster than Dijkstra, but only by a constant factor. It just cuts down the work in the wrong direction. So in the worst case, it will explore the whole graph. On average, it might explore only more like a quarter of the graph. But from a complexity point of view, that doesn't really matter. That's just changing the constant. So it's going to explore the whole graph. It's going to look at every node, or maybe a quarter of them, but we don't care for complexity. So that's V. And then you have to think of, well, what work does it do when it explores a node? So this is like testing how well you remember the code, but it basically checks, have I found a better travel time to this before? And if you properly implemented your A star, it should get the best travel time the first time it goes to a node. And then after that, it's just going to skip it, right? It's going to say, I didn't find a better path. It looks at, it puts it in the priority queue, and then later on, it'll take it out of the priority queue, okay? And that's it. That's the major work. It also looks at all the things it can reach from there, but that's constant time. So it does a little bit of constant time operation. The biggest thing it does is it puts each of these vertices into a priority queue, and then it basically takes them back out again in the right order. So what's the complexity to put things in a priority queue? What's the complexity to take things out of a priority queue? Do you remember? Anybody with me on this one? Yeah, so it's log. So it's log V. So that's the complexity. Okay, so you look at this and you go, could be reasonably large. Okay, we've got this K squared. K's not as big as like V, but still could be 300. And V can be pretty big. So this complexity looks moderately high. If you might go, maybe it'll work. If you try it, you'll find this is too slow. Okay, this is going to take for 300 interesting intersections. I mean, this is probably going to take you, 10 minutes, right? Like 10 minutes, 20 minutes, way more than our 30-second or 50-second budget. Okay, which isn't obvious from the complexity. You'd probably be concerned, but may not know it's going to be too slow. If you try it, it will be too slow. Okay, so too slow. And we talked about this in lecture. Well, let me go back for a second. Okay, so we'll see who remembers from lecture what we do for this. What can we do algorithmically to do better? So we came up with a technique where we changed our pathfinding to make this better. So what do we do? Anybody remember? Yeah. Right. Right. So basically, so that's exactly right. So we're not going to use A star anymore. A star is the fastest algorithm to go from one source to one dest because it understands which direction to head. Like it's smart. But if we want to go from one source to many destinations, which actually we're trying to fill that in this matrix. One row is actually from one source to all the destinations, all the interesting intersections. So we actually want to change our approach. We want to get rid of this inner loop and change this algorithm, okay? And that's what this does. It says, let's just do one loop over the sources, so over every interesting intersection as a start point. And we're going to write a slightly different pathfinding algorithm. It's not A star. It's now back to Dijkstra, and it's not Dijkstra to one destination. We're saying, find me the shortest path to a whole bunch of destinations. turns out Dijkstra naturally does that. I don't have to change very much code for that because it actually just searches the whole graph. It actually hasn't found me the shortest distance to one node. It's actually found me the shortest distance to all of them. So I'm just going to make use of that by writing a little more code. And so I pass in source, and I'm now passing in the whole vector of intersections. I'm not passing in, this is my source, and it's not just one destination anymore, it's a whole bunch. And I've gone off and I've written this algorithm. Still have k interesting intersections, still have v total intersections of the whole graph. Okay, so what's the complexity of this? Oh, spoiler alert, TAs love to ask questions like this in the final presentation. Okay, so actually being pretty good at this is a good idea. Okay, they like to ask, okay, why is this algorithm faster than that? Why is it faster than that? Can you talk me through some of the complexity? They don't expect perfect answers, but if you just say, I forgot what all the algorithms are and I didn't really pay attention to complexity, well, at least it's succinct, right? So they might give you something for, well, at least that was a succinct answer, but they're not going to be super happy. So what do you think the complexity of this one is? And a hint, it's going to be lower than what I just showed you. Otherwise, why do this algorithm? So anybody want to take a shot at this? This is like a practice for your final presentation question. Now everybody's more intimidated. That was supposed to make you more motivated to answer questions, not less motivated. So don't worry, there are no grades associated with this at this point. So, well, so take a look at it. How many loops? We start with complexity. You kind of go, well, let's just look at the loops first, right? That's easy. So what does the loop structure make you think you're going to have in this complexity analysis? Okay, so there's one piece of this complexity that should be kind of obvious. What do you think? Right, so this loop, outer loop is k. So we're going to have a multiply by k. Now we need to think of, well, then what's the complexity of this thing in the middle? Okay, and I kind of give you a lot of hints on that. It's a Dijkstra algorithm. Dijkstra has the same complexity as A star, because A star is just a tweak that makes it faster, but by a constant factor. This is Dijkstra to many destinations, but that doesn't really slow it down much. The only thing it slows down is it doesn't stop early. If you run Dijkstra and you find the destination, you can stop exploring. If you run multi-destination Dijkstra, you can't stop exploring until you found all the destinations, which means in practice, you're pretty much going to search the whole graph all the time if you got a whole bunch of destinations. But that doesn't actually change the worst case complexity, because the worst case before was you'd search the whole thing anyway if you were going from one source to something that was far away. So, okay, so we got a k. Given what I just said, what do you think the complexity of this thing is? Is it going to be the same as what we just did for A star? So yeah, it's going to be the same. Every vertex we can look at, and every one of them we're going to put in a priority queue and take out of a priority queue. So V log V. Yeah. Regular breadth first search will not, yes, there's two ways you can write breadth first search. The conventional way, like what most people mean when they say breadth first search, uses a visited flag, which means it will, and it explores now in a, not quite a random order, but it just explores in sort of a wavefront order. It just expands outwards, and whoever gets there first, they mark that node as done. So regular breadth first search would be fast. In fact, it does get rid of this log V, but it doesn't get the optimal paths. Okay, so you don't want to use that because you got rid of a log V, but you just threw away a whole pile of performance, which isn't a good idea. Then we did an enhancement to breadth first search, or a variation on it, where we allowed things to be re-expanded if we found a better path. That one is k times v times big, okay? The big is hard to bound. It's like, now we can't say that we just go to a node once, because we can re-expand it. And in practice, we can actually re-expand it a lot. So basically, it's no longer bounded by k times v times log v, or it could be v squared. I'd have to actually analyze it. I'm not even sure, but it's big. Does that make sense? It's kind of a function of the graph, but I'd have to think of what's the worst case graph I can produce, but it's a lot worse than v log v. Does that make sense? So the priority queue is your friend. It's making, if you want optimal paths, the priority queue is letting you do things in a very efficient order. So you only look at every vertex once, and you're not going to beat that. Trying to get rid of that priority queue is going to defeat. You will be sad. Don't do it. But anyway, good question. Okay, so everybody with me on complexity? All right, so it's a lot better, kv log v. All right, so you should use this algorithm. Why did I go through this? Because this is the algorithm we're going to parallelize in the later part of the tutorial. And it's also because I'm telling you about multi-threading, but sometimes people get excited about multi-threading and they go, what I should do is just don't worry about the algorithm, get that down really fast, and then just start parallelizing. That's the wrong approach. Get a good algorithm first. You usually get bigger gains, and it's easier. Parallel programming is hard. So don't do parallel programming first, do it last, okay? All right, so now let's talk about parallel programming. So in the UG machines, we have what are called 4-core processors. And in your laptop, you probably have something that is, if it's relatively recent, it's probably a 4-core processor as well, okay? It might even be 6-core nowadays. If it's relatively cheap, it might be 2. But it's rare to get a single-core processor nowadays, unless it's a very cheap microcontroller, which goes into things like washing machines, okay? So your washing machine has a processor in it. It's probably single-core, okay? But these TVs will be multi-core. Your laptop's multi-core, the UG machines are multi-core. So what does multi-core mean? It means in one physical chip, you have essentially more than one processor. But because that was kind of confusing, people used processor to mean chip. They came up with this new term called core. What core is basically all the execution engines for a processor. So each of these is basically, you can think of as a complete processor, okay? And they all share memory. Okay, so every core can execute its own instructions. It's got its own program counter, and it's got its own execution units to do multiply and divide and so on. But they share this common memory space. They can all get at the memory of the machine. Now you could say, well, let's say so far you've been writing single-threaded programs. On the UG machine, sometimes you were sharing the machine with somebody else. Okay, so somebody else could be running a program and you were running a program as well, or maybe you were running 2 separate programs. Those programs generally the operating system will try to run them on separate cores because then they'll both run fast. And they are sharing memory as well, but they're sharing what's called the physical memory. Okay, so there's only 16 gigs in the machine. They both have to share that. But the operating system basically just gives each program access to part of the memory. And if you ever try to access memory that's outside your part, the operating system kills you, and that's a seg fault. Okay? So yes, physically the memory was shared, but logically it wasn't. You could not access the memory of another computer. The operating system would kill you. So basically you had one processor and it owned all the memory that it talked to. Didn't have to worry about anybody else touching it. Okay, so does that make sense? And this is one of the things that multi-core processors are used for is, run multiple programs. So that's a good thing to do, and you've already been doing that. But now what we're going to do is we're going to try to write a program where we have more than one core that together are trying to make one program faster. And that's called multi-threading, and it's a little more tricky. I'm going to give you an overview of that in this tutorial and some more in the lecture tonight. If you want to learn more, it's actually a pretty big topic. So in ECE 344 operating systems, you learn what are these threads? How are they actually made? Because the operating system helps create them and do what's called scheduling them, so deciding when they run. If you take ECE 454, that's computer systems programming, that course is all about how do you take a program and make it run fast. So how do you multi-thread it? You saw probably earlier in this course that divide is slow. So, and you saw you could speed up programs by choosing appropriate data structures. So it's all about how do we write low-level code and multi-thread so we get the most out of a CPU. So you're really thinking about how CPUs do things. And ECE 552 is computer architecture. It's basically how do we actually build this? This is actually really complicated, okay? To have these multiple cores collaborating through this shared memory, and we also want them to be fast, so that's a big topic too. And this is an area of very active research. So, so you can go to graduate school, okay? So yeah, it's a big topic. I'm gonna talk about a little bit of it. Okay, so applications with a single thread. So I already talked about this. You've been writing these applications. Basically, in C++ and C, when the program starts, one thread is created and it starts executing main. Okay, so that's what all your programs to date, unless you've done some on your own time, have been doing. They have one thread and it starts running main. And that one thread basically just sees all the memory. Okay, it doesn't have to worry about anybody else touching the memory. Okay, So once we have multiple threads, so here's two cores, and they now, both of them now see the same memory, okay? And that's kind of the core challenge of writing multi-threaded applications, is thinking about what's going on in all this shared state, all this shared memory. So basically, multiple threads can modify the same variable. And that's a good thing in some cases. It means they can communicate very efficiently, right? So if this core wants to send some information to this core, it can write a variable and this core can read it. And that's actually very fast. So that's a good thing, really fast communication. The bad thing is, you need to be thinking about this. If this core is doing something like saying this maybe is a certain variable I, okay? And this core 1 goes I++. And let's say this core 1 also says I++. Maybe it's executing very similar code. And let's say initially I equals 0. What is I after this core and this core incremented? Well, if you didn't coordinate them somehow, and there are techniques to coordinate them, I could be 1, I could be 2. It could be 1 because one of them could be incrementing at the same time as the other, and its increment overwrites the other one. So in a serial program, this would never happen. You go, I incremented I twice, it was 0, it will be 2. If you have two threads and you do not coordinate them and they're both incrementing that variable at some point in time, there will be some cases where after each of them is incremented, it actually comes out 1, okay? And that can percolate through your program and cause complete chaos. Now, there are techniques, programming techniques, where you can basically make them synchronize themselves. So one of them checks, are you incrementing the variable? Okay, if you're not, I'll increment it. So if they both check that, they can kind of coordinate and you won't get this bug, but you actually have to write code to do it. Does that make sense? So that's kind of the fundamental thing that can go wrong, is this shared state. So let's start with a simple parallelization example. So here's a loop, goes from 0 to 100, and all it does is it computes an output vector, C, that is the sum of two input vectors, A and B. Okay, now first thing to note, well, actually, let me show you how it's parallelized. So there are a few different ways you can create multiple threads in programs. So in C++, there are 3 different ways that are common to create threads. I'll talk about those 3 ways briefly in lecture. But the easiest one, the highest level one, is called OpenMP, Open Multiprocessing. So that's what I'm going to show you here. The other techniques are just basically lower level. You do more work. This will essentially call the lower level techniques for you. So you're working at a slightly higher level of abstraction, which usually makes you more productive. Okay, so let's look at this line. So I got a hashtag pragma. So does anybody know what hashtag pragma means to a compiler? So you'll see this sometimes in code. What is a compiler pragma? Does anybody know? So you've probably seen pragma once. So pragma once means, only include this header file once. In general, pragma means this is an instruction to the compiler, okay? And pragma once is a bit of an exception, but most pragmas, if the compiler doesn't understand them, it can ignore them and the program will still be correct. They're kind of like hints or extra guidance to the compiler. So this pragma says hint guidance to the compiler. OMP stands for Open Multiprocessing. So it just means this is going to be a pragma related to multiprocessing. And then this pragma's name is parallel for. And that's defined in a standard called OpenMP. What this whole thing means is if the compiler understands the pragma, the for loop that comes right after this should be executed in multiple threads. Okay, and that's all you need to do. The compiler will do the rest. It'll create the threads for you. It'll send some work to each thread. You could do that manually, but this is a lot less work. And almost all compilers are going to recognize this. If it didn't recognize this, it can ignore it, and actually the program's still correct because it'll just run slower. This would actually still work if you ran it in one thread. Okay, so what does that do? So on the UG machines, there are 4 cores. So OpenMP actually checks how many cores are there. It's going to find there are 4. So it's going to say, okay, I should create 4 threads. Well, I already have 1, right? There's the main thread of the program. We'll use that, but I'm going to create 3 more. And it's going to look at the loop bounds and it's going to say, okay, you got 100 iterations of this loop. So I'm going to send 25 of those iterations to the first thread, the next 25 to the next thread, and so on. Last 25 to the fourth thread. So it splits up the loop iterations. It sends them all off to these threads. So now we've got parallelism. All four of them are going to be working at the same time. We can get our answer faster. Now, in the serial code, like there can be some code after this, right? So maybe after this, well, there's some more stuff. Maybe I basically do a standard. Actually, I think I have that on the slide. Let me just click this. Okay, so maybe there's some code after this. Like I'm going to write out done. Okay. In the serial version of this code, this would never be printed until every single element of C had been computed, right? The whole for loop would be done. And then, and only then, would we go to the next line and print out this output message. OpenMP enforces the same behavior when it's using multiple threads. So it launches, you've got 4 threads running. They may finish at different times, right? For all sorts of reasons. You know, the 4 cores are slightly different speeds. Some data's in the cache in one, not in the other, whatever. For all sorts of reasons, one of them finishes a little before the other 3. None of the threads will be allowed to proceed onto this next line until all 4 of them are done. Once all 4 of them are done, 3 of them are basically either destroyed or suspended. It's called putting them to sleep. And then the last one will continue on. So what that means is it behaves just like it would if it was serial code once I get outside this loop, right? I'm going to wait till all the threads are done. 4 loops finished, I go on to the next instruction. Does that make sense? Okay, so OpenMP actually did a reasonable amount of work for us here. Created the threads for us, divided up the work, and did what's called the thread join. This is called a join operation. All the threads wait till they're all done. Okay, you can write that code manually if you wanted, but again, why would you? You just do this pragma and it'll all happen for you. Any questions on this? Okay, so let me point out something else. So I told you like kind of the fundamental thing. Well, I gave you that example of the shared variable I that I'm incrementing in multiple threads and how that's really bad. Like, or I need to produce some synchronization. I didn't write anything to synchronize anything here. This is just a regular for loop. Is it okay? So you have to look at this carefully. So when you use this pragma, you have to look at what's in your for loop very carefully. So is it going to be okay to have 4 threads splitting up this work and doing it at the same time? Or do we have some what are called dependencies? Do we have them updating the same variable at the same time? So what do you think? If you look at this code, so there's only one line. Is it okay? Here I've split it up and all 4 of these things can be happening at the same time. What do you think? Does it look okay? Okay, so you're nodding your head. And you're actually right. It is okay. Why is it okay? Just feels good? Not sure? Right. So that's exactly it. It's because every one of these CIs that we're computing, it's different in each thread. There's no dependency between them. If I actually change this code to instead be something like this, okay, let me just write this in. So I said int sum equals 0. And then in here, I didn't say this. I said sum plus equals AI plus BI. Is that okay? Could I just run that in parallel across multiple threads? So what do you think? No, so you're right. That's not okay. The reason that's not okay is, well, all of these 4 threads now are all incrementing this sum variable, which is the same. That's chaos. That's the case I told you about where they're actually going to be overwriting each other and we're not going to actually get the right sum. Yeah.
So how do we know that we're not doing that with variable?
That's a good question. Okay, so I'll show you. Yeah, that's a really good question. Basically, the semantics of this parallel for are that any variables that are, actually I should change this, just put int I. Okay, so I'm going to put an int I in there now because I think the way I've written it is actually dangerous. So good catch. So I should declare it in here. All the local variables, the variables you declare inside that parallel for or are declared in any function that you call from it are separate per thread. Every thread gets its own copy of the local variables that you created essentially within the parallel for. And if you call functions, those are considered in the parallel for as well. Does that make sense? So yeah, when you look at this, and I should put this int I in, because I think actually without the int I, like if I actually declared it out here, it's not good because I made one copy of this loop counter variable, so that's not good. I think actually OpenMP may special case the case of the loop control variable because it knows it always wants a copy per thread, but it would be more clear if I put an int I here. So I'll put that on the slides. So consider there to be an int I here, so I declared it. Does that make sense? So every thread gets its copy of the variables that are declared in the parallel for or in functions that it calls. So you don't have to worry about those ones. All right, so yeah, so that's why this one works. Okay, so let me go quickly demonstrate this. Okay. And I posted this on Piazza, but basically we figured out this tutorial is longer than an hour. So hopefully you still have time. If not, it's recorded because I'm not going to get through everything in an hour. Let's see. Okay, so let me show you the code here. Tell me this is big enough. Oops, that's the executable code. Can you read that, or should I make that one bigger? Looks like maybe I should make it one bigger. Let's see, what's the font? All right, how's that? Is that easier to read? Okay. Okay, so this is a little program that demonstrates use of OpenMP on basically a loop that's very similar to what I just showed you. Okay, so this is the length of vector. Let's cut this down to size a bit. So 10,000 elements in a vector. And I make 3 vectors, A, B, and C, all of 10,000 elements. I initialize A and B with just some random data. And then I'm using chrono to get the time, because I want to time this loop. And I have this parallel for loop. Okay, so I'm saying the loop after this is going to be run in parallel across multiple threads. I'm going to go through the whole vector, so from 0 to vector length. I'm going to ask OpenMP, tell me how many threads there are. I would normally put that in my code, except I want to show you the number of threads. Like I don't actually need this, I just want to demonstrate. And then I basically compute a value of this C array, which is only a function of A and B. Okay, and actually a function of A and B of the same indices. So there's none of that problem. I'm going to be updating the same variable in different threads. I'm not just adding them, I'm doing a bit more work, some multiply, some divide, some modulus. It's just to slow things down. Addition is so fast that it's difficult to do a demo with that little work in a for loop. So this is the same idea, but more work. Okay, then I get the end time and do the chrono code just to basically print out how much time has passed for this loop and the number of threads. Okay, so I'm going to build this. I think I want to. Okay, so I'm going to build it. I should always build release when I am going to time things. And let's see how long it takes. Okay, so it was really fast because 10,000 iterations through a loop isn't that much for C++. Can you guys read this, or should I make it even bigger still? It's okay? All right. So the time is fast. It's about 60 microseconds, and it used 4 threads. Okay, so 4 threads use 60 microseconds. Okay, so now I'm going to go in. I'm going to comment out this parallel for. So I just changed it back to serial code. By doing that, I'm going to do my make command again. Okay, and let's run it. Okay, so it was 60 microseconds, and now it's like 53 microseconds. It's actually a little faster, and it only used 1 thread. Okay, so that was disappointing, right? So using 4 threads actually slowed this down some. 1 thread, you look at this, that's 53 microseconds. You look at the 4 thread case, it was 60 microseconds. So it's a bit slower with 4 threads. What happened? It means parallel processing doesn't work. End of tutorial, go on with your day. I see some of you going, please, please, please let that be the answer. So, but that's not the answer. Yes.
It probably takes some time to set up the thread.
Yeah, so there's overhead. So setting up a thread takes some effort. Okay, you have to Well, it's basically, you'll learn this in operating systems, but there's a bunch of bookkeeping to set a thread up. So I created 4 threads, but they don't have that much work. Going through 10,000 elements of a vector is not that much work, so I didn't pay for my overhead. So let's go in and just make the vectors longer. Let's see what happens. Okay, so wasn't worthwhile with 10,000 elements. Let's make a big vector. So that's 1,000,000. Okay, that should be 1,000,000,000 if I didn't miscount. And let's just run this. This is the serial version. Okay, my OpenMP is still, Parallel 4 is still commented out, so it's just running 1 thread. And it's going to take a few seconds now because it is doing 1,000,000,000 calculations through this vector. And let's see what it says. And if I put an extra 0 in there, then it's going to take a really long time. So hopefully I didn't do that, but I think I didn't. So should finish any moment, or I'm going to go back in and take a 0 out. So. Yeah. Sorry, can you say it again? Yeah, it's a good question. So I'm going to show you that towards the end of the tutorial. The debugger has another window in it. If you go window debugging, there's a window called threads. Okay, and you can use that to switch between the threads. Debugging multiple multi-threaded programs is fundamentally harder because instead of thinking about my program does this, you've got like multiple threads and they're all doing different things. It is a harder thing to do, which is why you don't write multi-threaded code till the serial code works well and you go, I got some time. Okay, so it took longer than 5 seconds, but it's because I'm only timing the loop, right? The setup code I'm not timing. So it took 5 seconds, and that was with 1 thread. Now let's go in, let's do this again, and let's turn on parallelism. So remember 5 seconds, and let's see, if I use exclamation point, it repeats the last command that matches that, so I just did make again. And if I hit tab, file name completes. So I'm telling you guys that in case you don't know it. I often see students not using the command line super efficiently. Okay, now it took 1 second. Okay, so I actually went from 5 seconds to like 1. So actually better than a 4x speedup, which is good. I would expect kind of best case of 4x speedup. This does happen sometimes. It's called a super linear speedup. It's usually because of, in 243, have you studied caches yet? Do you know what a cache is? So usually it's because once I go on 4 cores, I actually get access to 4 first-level caches. So I can actually sometimes get more than 4x speed up because I'm not hitting main memory as often. So each core actually also gets faster because they've each got like a piece of the data, if that makes sense. And it actually fits in their caches better. It's like a happy situation, does happen sometimes, doesn't happen most of the time. So, but I got even better than 4x speed up. So it was great. Okay, so any questions on that? So it's not much code to write with an OpenMP. And for a simple loop, I got a pretty nice speed up. Make sure you got enough work. Okay, I'm going to flip this really fast. This is just some measurements on as you change what's the speed up? Speed up is just time of the serial code divided by the time of the parallel code. And basically, as I made it bigger and bigger, the speed ups went from terrible to quite good. And I went even bigger than this. When I went to 1 billion, I actually got a speed up about 5. Okay, so yeah, key lesson from that, make sure you got enough work. Okay, let's talk now about milestone 4 and fast pathfinding. So I'm taking the results from the Toronto Easy test case. Toronto Easy test case has 25 pickups and drop-offs, so 25 deliveries, and 2 depots. That means there are 52 interesting intersections, right? 2 times 25 plus 2. So my K is 52. And if I take my best milestone 3 algorithm, A star, and I just run it K squared times, for every source and destination, it took 32 seconds, which is not great. It's not great because I only have 50 seconds. This isn't the biggest problem. So it's going to be too slow when I give it a big problem. If I change that to that multi-target dijkstra, I only invoke that algorithm instead of 52 times squared, 52 squared times, I only invoke it 52 times, and I get a big speed up. So it goes down to 5 point something seconds. And the speed up is just the ratio of these two runtimes, which is 5.5x. So that's pretty good. Now I could actually take this A star algorithm that I was running k squared times, and there's lots of parallelism, right? I got k squared different invocations of this algorithm. I could run some of them in parallel. If I do that, it does go down in runtime. I get a 3.5x speed up. That's more typical. Usually when you write parallel code, you got 4 cores, you won't get 4x speed up, but 3.5 is pretty good. Okay, the reason you probably didn't get 4x speed up, some overhead, and there can be contention in the memory system, right? So sometimes you win because you get more access to caches. Sometimes the contention where multiple cores are trying to access main memory at the same time, they compete, they don't get 4x speed up. So this is pretty good. But it's actually not as good as what I got from changing the algorithm. So again, illustrates change the algorithm first if you've got an idea of how to improve it. And then the last row here is what if I do both? I use my better algorithm, multi-target dijkstra, but I make it parallel. And if I do that, I get the runtime all the way down to 1.8 seconds. It's about a 20x speed up. And now this one is fast enough that I could actually take all the problems we have, and it's going to be fast enough so I could use it all the way through. So that looks pretty good. So yeah, that's the takeaway. Tune the algorithms first. Then if you have time, you can try parallelism. Okay, so how are we going to parallelize this? So here's my multi-destination dijkstra, and this is basically like pseudocode, okay? Like I've left out anything I felt like in order to fit it on the slide, so this is not going to compile. What have I got? So remember we had a couple key variables that we needed to do our dijkstra or A star algorithm. So we needed the wavefront, which was like our to-do list. What nodes have we reached, but we haven't explored beyond them? And we needed this vector of nodes, which is basically storing how did I get here? You know, what's my reaching edge? What's my best time? So some information about whether I've gotten to a node, and if I did, what was the time and what was the previous node? How did I get here? And now I put in this third data structure, which is just a list of I've got these k interesting intersections. This vector just says what they are. Okay, so for the case I just showed you, this vector would have 52 things in them. Those 52 things would be the intersection IDs of all these pickups and drop-offs and so on. All the things I'm interested in. Okay, so I'm going to go through, and I'm going to use multi-destination dijkstra. So I'm going to go through this whole key intersection vector, 52 things. And for everything in it, I'm going to say from that source, so that's the ID of the, this is where I want to start from. ID of the source intersection. Go to all the other interesting intersections. So call my multi-destination dijkstra and do that. Let me do a quick aside here. The notation I'm using here, because it's nice and compact, is called a range-based for. So it's another piece of C++ syntax. It looks a little bit Python-like. Don't be confused by it. It basically does exactly what you would think. This just basically iterates through this whole vector. It is identical to this code. So the compiler basically pastes this code in for you. So it's just like a shorthand. So it's like I said, go through this whole key intersection vector. So from 0 to size, go through the whole thing. And for every single index I, get what that index I will get what is at that index value. Okay, and we're going to call that the source. So this is a shorthand for that. It just says loop through the whole vector, get every element, one element per iteration through the loop, and call that element source. So it does exactly what I put on the right-hand side. Okay? All right, so I go through this. I'm going to call my multi-destination dijkstra, and I've called that function find paths, and it's down here. So find paths takes the ID of the source intersection, and it takes a vector of the destination intersection IDs, and it's going to do a dijkstra algorithm, which somewhere in it is going to have a push into the wavefront. And it's got lots of other code, which I'm not showing you. So is everybody with me? All right. Whoops. So that was too many clicks. Okay, so to make this parallel, I need to put this pragma OMP parallel for in front of my for loop. And you know, this for loop, it looks pretty parallel. I've basically got a whole bunch of these source intersections that I'm searching from this start intersection to all the other interesting intersections. Those look pretty independent. So put parallel for in front of them. Hopefully this is faster. So what do you think? Is this going to work? Or do you see it? Okay, so I see you shaking your head. What are you worried about? Right. Yeah. So this nodes variable is going to be a problem. I've made a global nodes variable. I'm going to have 4 different threads. I'm going to divide this work across 4 cores. All of them are going to be using the same nodes variable. They're also going to be using the same wavefront variable because I made that global too. So, and I basically showed you just one line of code that I'm pushing things into this wavefront. Okay, well, I've actually got 4 threads pushing things into this wavefront, starting from 4 different sources. And I've got 4 of them updating the nodes vector with like, what's my best path? But they're actually talking about the best path from 4 different locations, and they're just writing on top of the same data. So it's like complete chaos. Okay, this is not going to work. I have what are called race conditions. I basically am writing to shared memory in multiple threads with no synchronization. It's madness. Okay, no good will come of this. Trust me. Okay, so does that make sense? Everybody sees why this is broken? Like this is like really broken. Okay, it's. If you run this, like it will be so chaotic. It will make your head hurt. I am going to run it in a little while, but you're going to see that like it's just chaos. You can't reason about it. Okay, so these shared globals are a big problem. I got to get rid of them because I'm modifying them in multiple threads now. So to get rid of them is relatively easy. There's no particular reason that I had to make these globals. I can just take these variables and don't declare them here, declare them here. Okay, I didn't really need them to be global. So once I've done that, so notice I've just moved the declaration into find paths. Find paths is called from within my parallel 4. That means that every variable it creates is local to a thread. I've already created multiple threads. They're all going to call find paths. Every variable is declared inside there will be separate, different copy per thread. Does that make sense? And that's actually all I needed here. I don't want communication. I want these to all be separate. So just by moving the declarations, I did that. Does everybody get that? This is actually one of the reasons global variables are, they're not the first thing you should do, right? There was no reason for these to be global. If I make them local, this code is actually ready to multi-thread. If I have them global, I've created essentially a false dependency, and I can't make my code parallel. I got to fix that. Okay, so this is sometimes called privatization. So privatization basically means every thread gets its own copy of this variable. Does everybody understand this? This is like the key technique for what you're going to have to change to make things parallel. Okay, so it sounds like you're with me. Okay, what about this one? Whoops, I screwed up the animation. So you kind of know the answer. So if you can read, see, here, I'll scratch that out. There, now you can't tell the answer. Is this okay? So I moved 2 of these global variables down here. They become local variables. What about this one? I've got this key intersections. That's my K intersections of interest. Do I need to move that, somewhere in here? Or maybe in here, its declaration? Because right now it's going to be shared across all threads. Yeah. 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 And that's exactly right. You're right. The answer is kind of like, well, how to use it? But it turns out that when you write multi-destination dijkstra, like there's no reason to ever take anything out of this. This is just like a list of it's a list of all the interesting intersections. I don't need to modify it at all in my dijkstra algorithm. So because this one, if you write your code in a conventional way, will not be modified inside these threads, it's okay. So memory, it's okay to have many threads reading the same memory. That's fine. The only problem is when at least one of them is writing. Well, so if 2 of them are writing, they can overwrite each other. If one is writing and others are reading, that's also a problem because basically they can read data as the other one's halfway through writing it. So if anybody's writing, it's not okay. If they can all get at the same variable and there's no synchronization. But if they're all reading, that's fine. So this is a variable that I set up in advance, but they're all reading it, so it's fine. So this means in this wavefront algorithm, we've got all sorts of information that we created in load map. We've got information from streets database, but it's all just red. Aside from these variables, your Dijkstra's algorithm is probably not changing any major state. All of the other stuff from streets database, your milestone 1 APIs, is not being changed by the thread, so it's fine. They can all just use the same data. Does that make sense? So you don't have to privatize everything, just things that people are writing to. Okay, so what about this? So here I had global variables. We said those were a problem. So, but now I'm basically showing you a little more code. I'm making this code that loads my matrix of delivery times. I'm calling it preload time matrix, so it's in a function. And it takes in, some information, deliveries and depots. It's going to use those to figure out what these key intersections are. So it does that. I'm not showing it. And then it calls, the parallel code to do pathfinding. So I don't have global variables anymore. I am declaring my priority queue and my nodes here. So there are local variables in this function. I haven't bothered updating this, but basically they'd have to be passed in. Whoops. So let's pretend that I did this properly by passing in the wavefront and the nodes. I'll fix that afterwards. Is this okay? Okay, so they're not global. They're local variables. They're local variables in this routine. They're passed into find paths. Do you think that would work, or do you think that would not work? Okay, so what you have to think about is, did every thread get its own copy of these, or are they all still sharing one copy? So what do you think? What would make sense here? I don't know the exact rules, but I guess what makes sense to you? Yeah. Yeah, but I probably can't. Well, that's a good question. So this passed by value. Yeah, so that's actually true. If I pass them by value, it would be okay. These are big though. So do you think I'm probably not going to pass them by value? So yeah, okay. So it's actually a good answer. So if I pass them by value, you'd be okay. But they're big, so I don't want to. So I pass by reference, which is not good enough. Okay. So then everybody still gets the same copy. So it's not just locals or it's not just global variables you have to watch for. You have to watch for, if I passed a local variable by reference as well, then every thread's got it still pointing at the same copy, and that's a problem. Does that make sense? That's actually a really good answer, though. I didn't think about that. They're so big, I never thought of passing them by value. So I guess I should write in exactly what I'm doing here, because if I pass them by value, it would be okay. So yeah, global variables aren't special. It's basically what am I creating and passing pointers to, or their global variables. Okay, so let me go and quickly do a demo of this. Okay. Okay, so this is the reference solution that the TAs and I have created for the course. And you're not going to understand it all, which is fine. This is basically filling in that path matrix. Okay, so you don't have to worry about understanding all the code, but it's basically doing what I just showed you. And let's see, it is doing it with a parallel 4. So it's basically going through and calling a multi-destination dijkstra, and it's been parallelized exactly the way that I just showed you. Okay, so if I go into this multi-destination dijkstra, just want to go take a quick look and see what I've got set here. It's if not def bad parallel global. Okay, so I want to go and make a change here because I want to show it working first. I've basically got some defines in here so I can change between global variables and local variables. So I can kind of do it the right way or the wrong way. And I have to remember which one is active right now. Okay, so I'm going to comment this out. Let's see. Okay, so those are commented out. So that sounds good. Okay, so this should work now. And actually, I'm going to change it to, so I'm going to change this to release build and just build it. And once it's done, I'm going to go out and I'm going to run one of the 297 exercise cases. We'll see how long the pathfinding takes. And then I'm going to turn off the parallel 4 and we'll see how long the pathfinding takes when I do that. Okay. So that's the first thing I want to demonstrate. Okay, so I built it and I built release. I don't want to run all the testers because it's going to take too long. I just want one. So let's see. So I listed all the testers. I want to say, let's run. So let's run one that has easy Toronto in it. And like I said, that should be that 52 interesting intersections case. It should be 25 deliveries, 2 depots. Okay, so it's going through my load map. Load map is just telling me what it's found in Toronto. And in a minute, it's going to get into, okay, so it started doing the optimization. And it basically says it finished all the pathfinding, which is that load.matrix in 1.82 seconds. So pretty fast. So I'm going to stop this. You can see our reference solution actually uses annealing. So it's like you don't have to use, but yeah, that means we do use annealing. So we combine it with a few algorithms. So we actually combine it with pretty much a little bit of every algorithm we showed you. Let's see. So I think I went to the wrong spot. Let's go back here. Okay, so I'm going to go back in the code and I'm going to make one change. I'm going to turn off the parallelism. Okay, so just one line to do that. Still compiling release build. And then I'm just going to go run that command again. We'll see how much difference this made to my pathfinding runtime. Okay, so you can use the up arrows to go back to an old command. Okay, so I'm going to run this again, and you have to remember 1.8 seconds. That's how long the parallel version took. Let's see how long the serial version takes. Okay, so serial version took 5.8. Okay, so about 3 times slower. And for bigger problems, the speed up's a little more. Okay, so this makes us faster by about 3, maybe 3.5 times. Doesn't quite get us to 4. The pathfinding algorithm uses a lot of memory, so you get some contention accessing memory. You don't quite get to 4x speed up. But it's pretty good. And you can see it wasn't much code, right? Like I just turned on that OMP parallel 4. Okay, it wasn't much code because we didn't use shared state like global variables and so on. So if we had, then we have to do some rewriting. Okay, so we talked about this a few tutorials ago, but if-defs are basically, they're called preprocessor directives. I can basically tell the C++ preprocessor, which basically goes through my code doing cut and paste. Like if I define a variable here, I can tell the C++ compiler that I want to bring some code in or out. Okay, so I just defined this thing called bad parallel global 2. That sounds bad, and it's because it is bad. Okay, so let me show you what it does. Okay, so that's commented out. You can see that this global variable declaration of my priority queue is gray because it's not active. Now I uncomment it, and this becomes active. So what I just did, I put in the code these if-defs so that with this one line, I just changed my priority queue from a local variable, which is the right way to do it, to a global variable, which is the wrong way to do it when I'm running parallel code. Okay, so let's see what happens now. And I already know what's going to happen. So I'm already going to save time by switching to unit test debug. I've copied over that Toronto easy unit test, so it's already there. You'll see the compiler is actually giving me some warnings. They weren't there before. These warnings are, it's basically saying essentially my variable naming looks kind of bad. It's like I found a global variable here and a local variable there with the same name. So if I was writing this code for real, I'd go look at those warnings because the compiler is telling me your code's a little dodgy. And it is a little dodgy, but I did it on purpose, so I'm ignoring the warnings. Okay, so now I'm going to fire up the debugger, and we're going to see what happens. Okay, so the debugger is running on the unit tests. Actually, I'm doing this in the wrong order. Actually, let me stop this. I'm going to just do it in the right order because it'll be a better demo. Okay, because I still have parallelism off. So I got to go back and turn it on again. Okay, so I turned parallelism back on. So let's build this again. Okay, so I just uncommented the pragma OMP parallel 4, so I have parallelism on again. And then when this is done, I'm going to start debugging. Okay, so it's not release build, so it's going to take a little bit longer, but it's parallel. But I took my wavefront and I made it a global variable, which we already said is not a good idea. I'm going to have 4 threads now, all trying to access the same wavefront while they're trying to do different things. So there's no possible way that can work. Like you just go, that's madness. This is like, you and 3 of your friends are all in different courses trying to write one exam, but we just give you one keyboard and you all are just typing on it at the same time, trying to fill in your exam. And you're not allowed to talk to each other. The odds of you successfully doing the 4 exams are like 0, right? Like you're going to turn in one exam paper that is just gibberish. So that's what's going to happen here. Okay, so we're starting the traveling courier problem. So the first thing it does is this pathfinding to load up the matrix. And this should take, so in release build with parallelism on, it took 1.8 seconds. Debug, so maybe it's going to take, I don't know, 6 seconds, maybe 3 times slower. But it's taking a while. Okay, so how long have we been waiting now? Okay, I'm going to count to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, this is like too long. Okay, so this should not be taking this long. So I'm going to hit the pause button. Basically, it looks like the program's hung. I appear to be in some kind of infinite loop because this is taking too long. Okay, so I'm going to pause and I can go look at where I am. Now, you see down here, there's this new threads window. That wasn't there initially. To get it, you go Window, Debugging, Threads. Okay, so I turn on the Threads window. And now I go look at threads. The bolded thread is the one that the debugger is showing me right now. It, by default, tries to show you what it thinks is the most interesting thread, which means if your program's crashed, it'll show you that one. In this case, the program hasn't crashed, so it just showed me a random thread. And you can see there are 4 of them. So there are 4 threads active in my program now. If you ever bring up this thread window in your program when it's single thread, you'll just see 1 thread. So I see 4. Okay, so I can click on this one, and I can look at its call stack to see where is it. So here's the call stack. I want to look at a routine I recognize. So I'm going to go, that's priority queue. Let's see how that was called. So I'm here. I'm trying to get something out of the priority queue. So that's what this thread is doing. Let's go look at another thread. Okay, so that was the first thread. Let's go look at the second thread. Second thread is trying to get essentially the best time from the nodes array. Let's go look at the third thread. Third thread is trying to, it's in the priority queue as well. It's trying to pop something. Okay, so it's trying to take something out of the queue too. So 2 of them are trying to take something out of the queue. That's what I've seen so far. And let's see what the 4th thread is doing. Okay, the 4th thread is trying to check if the queue is empty. Okay, so we call it traversal queue means wavefront. So we just use a different name in the reference solution. So 3 of my 4 threads are doing something with the priority queue. Okay, 2 are trying to take something out. 1's trying to check if it's empty, and it appears to be hung. So let me just keep running this for a while. We'll see, does it ever come back? Whoops, I actually restarted it, so I don't want to do that. Okay, so let's not do that then, because it is hung. Actually, maybe we'll run it one more time. So it's hard to debug multi-threaded code because I actually know that I made a huge mistake here with one wavefront. The signal I get is just 3 of the 4 threads are in the wavefront and the program's hung. It's actually hard for me to figure out then that the way I'm using the wavefront is totally broken. So it is difficult to debug multi-threaded code. I'm running this again. The reason I'm running it again is because there are race conditions. Like what happens to my program now is a complicated condition of which thread does what first. Because I have this shared data that I'm accessing without any synchronization or control or anything. So that means that what happens in my program can actually vary from run to run, which also makes debugging harder. So with multi-threaded programs, it's actually common that you say, I ran it once and it got the right answer, and then I ran it again and it crashed, and I ran it again and it hung. Computer's broken. Computer's not broken, your program is broken, because it's actually behaving non-deterministically, which is normally a sign of a race condition. Okay, so this one's hung again, so it looks like it's usually hanging. So let me go back. So one of the things you do when you're debugging parallel programs like this is you get your serial version going first, And let me look for my OMP here. That's weird. Okay, let's go find the parallel 4. All right, there we go. Okay, I'm going to turn off parallelism. So I'm going to stop the debugging. Okay, so I've turned off parallelism, I rebuild, and I'm going to run this again. Okay, now why am I doing that? Because if you have parallelism and your program's behaving erratically, one of the first things you want to check is it the parallelism? Because then you can really zoom in on, you've got a problem, you've got some race condition where you're accessing data in an invalid way for multiple threads. So I run this again. If this works, then I say, okay, well, my problem's in the parallel code. If this doesn't work, then okay, my problem's in the serial code. So I've done like wolf fence model of I've kind of eliminated a lot of hypotheses right away. Does that make sense? Okay, so I just turned off parallelism, and now this should work because I'm using a global variable for my wavefront, but if I only have one thread, that will work. So, I might have had this working before. I put parallelism in, it doesn't work, turn it off, see if that's the problem. Okay, so it did work. Okay, it took 18 seconds because it's debug build and there's no parallelism, but it did work. Let me go and show you the, okay, so I told you that I have 2 different global variables that I can mess around with here. There was the wavefront, which I can make global, and I shouldn't do, but I did it. Okay, and there's this other one, basically my nodes vector. Okay, storing the best time to any node. So let's turn off this wavefront one and make it local again. But I've made my nodes vector, which in the reference solution we're calling all nodes. I've made it global. And that's also really bad. Yeah, let's see, where is this? Okay, there's M4. Okay, so I've turned parallelism back on. I've made my wavefront local, but I've now made my nodes array global, which is also going to be bad, but in a different way. So let's run the debugger. Okay, so it crashed. Okay, so now I got a crash. I hit discard and pause so I can go look at it. And let's see if I can bring this files display back. Let's see. Maybe I can't. All right, whatever. So I'm going to bring my threads display back. So go window, debugging, threads. Okay, and let's see. So here's my threads window. Okay, so this bolded one is the one that the debugger is showing me right now. And it picked that thread because it's in raise. Raise is a signal. It's like it's an interrupt. It basically says this thread has died and it's told, the operating system I'm dead. So it's showing me that because it says that's probably interesting to you. So I can go look at that. And there's a bunch, I need to get back to something I recognize. So I go back up the call stack to see where was I. I was trying to do a resize. Okay, so I'm actually doing something with all nodes. All nodes is my nodes vector. Okay, and I was trying to resize it and I crashed. So that's kind of interesting. And let's see, I'm gonna go back to my threads window. Okay, let's look at a different thread. So I'll look at this one. I'm looking at its call stack and let's see where I am. Okay, so it was way back here, which is interesting. So it basically hasn't really made much progress. It's actually right at the start of calling these routines. So let's look at the next thread. Okay, so if I look at the third one, and I just double clicked on it to bold it, I'd like to go to it. Where is it? Okay, oops. It's trying to, let's see, path. It's trying to modify the final path. Okay, so it's in a different spot too. And let's go to the last thread. Okay, and let's see where this is. Actually, this is near this is messing around with the priority queue. Okay, so this particular one now, so it's crashed in a different way. The one that crashed was accessing that nodes vector that I made global. The other ones, none of them were doing anything with the nodes vector, but basically they've managed to corrupt the nodes vector. So the memory's corrupted enough that one of them crashed when it actually tried to do a resize operation. So I guess the highlight of this is it is difficult to debug parallel code. When I'm looking at the threads, I can only kind of get an idea of what's going on. If I go look at the state inside there, I'll see, okay, it's kind of corrupt. How did it get corrupt? It's complicated. Probably two threads were trying to update something in the vector at the same time, and they each partially updated it, and it basically became so chaotic that we crashed the next time we tried to do something. So yeah, so any questions on that? That is how you debug parallel programs, but it is hard. The debugger will show you all the threads. One of your techniques is turn parallelism off, see if the problem goes away. If the problem changes every time you run, that's another sign it's probably a race condition. Finding race conditions is hard. You look at where the threads crashed. If they keep crashing in sort of this variable, then that's probably a race condition. But it can be more subtle than that, right? Because you can corrupt all sorts of stuff. Okay, so last few things. Is this code okay? So now I'm looking at this preload time matrix. And I'm calling my matrix paths. So it's just a vector of vectors, right? That's the whole thing I'm trying to load. I'm basically doing it in parallel. And I've been calling this find paths routine, which basically gets me an entire row of that matrix, okay? So that's what this does. It returns a vector of paths. It's like one row of the matrix. From this source to every destination, return a vector of all those paths, okay? So this, we've already talked about. Let's say we got that right. So that's now working. Let's just look at this part. How do you feel about this code? This is the code now that's calling that routine, and it's loading the matrix. So we get one row with every single call. So we're just pushing it into the back of this paths matrix. So this paths matrix basically is a vector, and every element in the vector points at another vector, or is another vector. So we're getting, every call is getting one of these things, and we're adding another row to our matrix. So basically every call is putting one more element in the first thing, and the first thing the first dimension, each element in it contains an entire row. So we're kind of pushing back to create one row at a time by just capturing what comes back from this find paths routine. So what do you think? Do you like this code? Any thoughts? So this code will work fine if I haven't actually typed it in the compiler, but it should work fine as long as I didn't make any stupid mistakes with one thread. So will it work with multiple threads? So you don't think it'll work with multiple threads. Why not? Yeah, so this is not good parallel code, okay? So in the serial code, we basically start with like an empty matrix, and we're basically using pushback to add one row at a time, and that'll work, okay? We know which row. The third time we go through this loop, we will get the third row, we will push it back, it will become the third row of the matrix. It's all good, okay? When we run this in parallel, these things are gonna come back in an arbitrary order, right? You saw how OpenMP splits up the work. It will split up, for example, the first 14 rows may go to thread 1, the next 14 to thread 2, and so on. So we're gonna get row 1, or let's say row 0 coming back. Then we might get row 15. Then we might get row 31. Then we might get row 1. It's chaos, right? They're going to come back in some arbitrary interleaved order, and it'll change every time. So if you try to debug it and you kind of carefully figured out like which row is which, you run it again and suddenly they come back in a different scrambled order. That again is a sign of a race condition. So yeah, this is not good because we're updating this path shared variable in multiple threads, and that's not safe. Okay, so it won't work. There's two problems. We just talked about the pushback one. It also can actually crash. The reason it can crash is, remember, pushback Sometimes this vector won't, this paths, the first dimension of it is a vector. So we try to put a new row in. Sometimes there isn't any room in the vector, right? And it needs to reallocate itself and get more capacity. If that happens while somebody else is trying to write a row, I mean, it's chaos. Somebody's in the middle of like copying everything and reallocating it. And while they're doing that, somebody else is trying to update the data that the first thread is trying to move. You have no idea what will happen, right? So it can corrupt memory, it could crash right there, etc. So, and it might happen sometimes, and other times it might turn out that there's never a reallocation right when somebody's updating, so it doesn't crash. So again, difficult to debug, and it is not going to work. How should we fix this? So it can be fixed. Yeah, what do you think? Yeah, that's exactly right. So basically, if we resize, use resize to basically create the entire first dimension. And the whole first dimension now is like it's an empty row, right? There's an empty vector in every entry, but it now exists. So this resize created this whole thing. That was done before we hit the parallel 4. And then in the parallel 4, every one of these calls is trying to basically capture a row, but it's trying to capture a row in one element of this vector that already exists. We will not get a reallocation of this vector because it's already the right size. And there's no pushback, put me in the next entry or anything like that. It's everybody's going into a different entry. Those entries all exist. It's going to work fine. Okay. So in this case, like the code we had to write wasn't much. It's just thinking about it, right? Like if you did not see this issue, then this can be a challenge to figure out what is going on. Okay. Okay. So debugging parallel programs. One important technique, use the wolf fence method right away. Turn off parallelism, see if it goes away. If it does, you have a very, very strong indication this is a race condition, and that's what you should be looking at. So shared variables that you're accessing in an undisciplined way. You are probably writing to a shared variable somewhere. You can then, that's the first thing to do. Next thing, you can run in the debugger. So you can use window debugging threads to see the different threads. You can look at the call stack for each. You can look at the variables for each, and you try to figure out what's going on. Race conditions are hard to debug. You know, you're looking for, everybody seems to be in the same thing. This thing seems really chaotic. It's updating in weird ways. Okay, it's probably a race condition. Fixing race conditions, once you've found them. Best way to do it is to privatize variables. So meaning every thread gets its own copy of the variable. So if you can move the declaration of the variable into the parallel 4 or into the functions it calls, it's automatically private to that thread. That's the best solution. Sometimes you can't do that. Now for pathfinding, you can. Okay, so privatizing your variables is fine. It's all you need to do. It'll work. There can be things like, remember I showed you that sum. If we had this sum variable that was plus equals something, that can't really be privatized. You do need to have you're trying to create one sum. So you do want one variable for the sum of this whole array. So you can have cases where there's fundamentally a shared variable that you need to stay shared. And what you do in that case is there's another pragma called OMP critical. You write, and I'll show this in lecture briefly today. OMP critical, you can take any block of code you want. So it could be one line of code, could be a whole larger block of line of code. And only one thread at a time will be allowed to go into that. Okay, so that's how you can enforce, you know, this is some synchronization primitive, or this is a key variable sum that I'm going to be updating. Only one thread can go in at a time. And now you can make your program correct with these shared variables. It isn't as good a solution. So it's not like the first thing you should try because it costs performance. I mean, you could put OMP critical. So let's say I just did this. If I put this whole thing in a block, and then I put OMP, like pragma OMP critical. Okay, this is kind of messy, but let's say I put like pragma OMP critical actually around this whole thing. So I put brackets here. It'll work. I just made it all serial again. I said, run this in parallel, but every thread has to wait for every other thread for everything. There is no purpose to that, because it is basically just a complicated way to write code that'll run serially anyway. So you want to keep OMP parallel or OMP critical, you want to use as little as you can, which for pathfinding is 0. For some other things, you need it some, but you try to use it sparingly around the least amount of code you possibly can to get the best speed up. Okay, so does that make sense? There's actually a tool called Intel Inspector, which is kind of like Valgrind for threads. So there is also a tool that you can use that can help find race conditions. It is very useful. We use that tool to find a race condition in Quartus. So I led a project when I was at Altera to make Quartus parallel because FPGAs keep getting bigger and CPUs aren't getting that much faster. So we had 7 major algorithms that we had to make parallel. The most complicated was the placement engine, which is actually related to this class of algorithms. Placement and routing engine, so placement plus routing, which is pathfinding related to your milestone 3. In Quartus is 1 million lines of code. The inner loop, the key loop of placement is 10,000 lines of code, okay, or was 10,000 lines of code. So it's actually a lot of code to make parallel. The placement engine was made parallel by one of my engineers, who's a really good engineer, named Adrian Ludman. And it worked very well after it was done. But when we ran the regression tests, we had 10,000 regression tests that would run on racks of servers that would take about 4 days to run on, a couple thousand CPUs. And if we turned on the parallel placer, which was, optimizing a problem kind of like this with multiple threads, it would work on, out of 10,000 regression tests, all but 2 to 4 would work. Okay, 2 to 4 would crash. Which 2 to 4 changed every time we ran it? Okay, so it was actually very hard to debug. And it indicated a race condition, right? So the fact that it was different every time meant it was probably a race condition was something we missed. We found it with Intel Thread Checker, which is now called Intel Inspector. Otherwise, it probably would have been impossible. It was a really subtle race condition. This particular one was, it was occasionally the threads, that one of the threads that was actually doing work got so far ahead of the thread that was initializing the standard library that it actually started using standard library calls before the standard library was fully initialized. It was very rare because it's quite bizarre, but one of the threads essentially was, the operating system didn't give it any CPU time for a while. So yeah, that was actually what was causing the problem. It would have been incredibly hard to find without this Intel Inspector tool, which, as I said, is like Valgrind, but instead of looking for memory faults, it actually looks for, this looks like a race condition. It looks like these 2 threads are accessing this memory location in an unsynchronized way. Anyway, this course is not about parallel programming, so we're not going to teach that tool, but it's a cool tool if you ever get stuck on these. Okay, so last few thoughts on parallelism. So an important thing to remember about parallelism is Amdahl's law. So Gene Amdahl is a pioneer of mainframes, and he came up with this law. So let's say we have n cores, and we have a program, almost no program is completely parallel. There's almost always some work that's serial, fundamentally has dependencies. So we say F is the fraction of the work that is parallelizable, could be run on multiple cores. Your speedup is given by this equation, which is basically just it's essentially a weighted average equation. It's not a very difficult one to derive. So what it means is that your maximum speedup is limited by the fraction of serial work, 1 minus F. So let's say half your work is parallel and half is serial. That's what this line is. This blue line is 50% of your work is parallel. Even if I give you 65,000 CPUs, your speedup will never go above 2, because the parallel work basically takes now no time, but the serial work is still half your time. You're limited to 2x speedup. If your parallel portion was much higher, say 95% of your runtime was parallel, then you could get a 20x speedup. But that's the most you're going to get, even with 65,000 CPUs. So this is one of the challenges to make parallel programs really fast, is you got to get almost, if you got a lot of CPUs, not 4, but like thousands, you got to get almost all the serial code out of there, right? Even little bits of serial code will limit you. When they start running code on supercomputers, where they really do have 65,000 or 500,000 cores working in parallel, they have to go find almost every little bit of serial code and get rid of it, because they really want to get to these huge speedups. Anyway, what this does, though, is it means when you're looking at parallelizing some algorithm, think about how much of your runtime it takes. If it's not that large a fraction of your runtime, it's probably not worth your effort, because Amdahl's law means you won't get that big a speedup anyway. Okay, so parallel programming takeaways: improve your algorithm first, because it's usually a bigger reward, it's usually easier. OpenMP pragmas, which is what I taught you here, is a higher level, pretty efficient way to write parallel code, particularly when you're doing it to speed things up. People sometimes use multiple threads as a way to separate tasks For example, it's common to have a user interface thread and a compute thread in a program. And in that case, creating the threads manually can make sense because you might want that control. When you're trying to make threads so that you can speed up parts of your program, you can do it manually, but OpenMP is usually, it's considerably less code. Don't modify shared state. So privatize your variables so every thread has its own copy instead. You want to parallelize big chunks of work, not little ones, because there's an overhead to starting threads, and it's hard, right? So making programs parallel is an active research area. Even experts make mistakes. So for M4, it's pretty open-ended. So you want to get something simple working first. It's like intended to actually be a demonstration of agile principles. If you just decide I'm going to do every complicated thing I can think of, and I made a schedule, here's how it's going to go. This team member is going to do parallelism in one day. This team member is going to do the most complicated algorithm another day. Your life will be hard, right? So get something simple working and improve it. You want probably a simple travel time estimate to start with, probably just geometric distance. You want a simple algorithm like greedy to work, and return a legal solution. Make sure you pass all the tests, see what your quality is, and you might go, that's good enough. I'm going to submit it. Or you might go, it's not good enough, but now you're working from a functional solution, which is the right agile technique. Once you've got that working, you can try better cost estimates. You can use the pathfinding approaches that we've talked about. And I would go parallel only when you're pretty happy with everything, because it is harder. So you want to do it if you want an extra challenge to learn some more stuff, but not put it on the critical path of your project. Okay, and that's it. So yeah, it's a longer tutorial today. Hopefully that was okay. And for anyone who arrived after we started, you can come ask me questions, or I can repeat parts of it. So, okay, so thanks everybody. Yeah.
So when we're trying to privatize variables, isn't that sort of the same as just passing them by value? Because we need to make copies of